Okay, we have been discussing how to remove items, so basically nodes that are leaf nodes or nodes with a single left child or right child. In this case, we have to find the predecessor basically if we would like to get rid of an item with two children. So basically we just have to create a node T, temporary node, get predecessor. We just have to find the greatest item in the left subtree. So that's why I print left subtree. And I'm going to print out, just for sake of simplicity, that removing item with two children. Okay, and let's implement this get predecessor. It is very similar to the get maximum item method, because we get a node, and if this node dot get right child, why the right? Because the greatest item is the rightmost item. So if it's not a null, then we are going to call this method recursively. So get predecessor on the node dot get right child. And anyways, we are just going to return the node. So this is how we get the greatest item from the left subtree. This is how remove works for a binary search tree. We get the predecessor, then we set the data. So basically the node.set data is equal to the temporary node. So basically we get the data from the predecessor and we swap them. And then we have to call this node.setLeftChild, and we have to call this delete method recursively on the node get left child and temporary node.get data. Okay, so basically this is when we call, basically we get the predecessor, we swap the two nodes, and this is how we call the method recursively again. Because maybe we are going to end up with a situation like this. This is the aim. So let's test it. I'm going to create a tree with integers. For example, bst is equal to a new binary search tree. Then bst.insert, I would like to insert, for example, 1. Then, sorry for that, for example, 10. Then 5. Then 15. I would like to insert, for example, 3 and 7. So basically, there are two nodes with two children. So whenever I would like to delete the 10, then we would be able to get rid of it. Let's make an in-order traversal after the delete operation. As you can see, we removed the 10 because the 10 has two children. That's why this part is going to be called. And after replacing the 10 with the predecessor, then it's going to be a leaf node. So we swap the 10 with the predecessor. Let's take a look at it. I would like to print out the predecessor here. Predecessor is plus the node, because the predecessor is the greatest item in the left subtree. Okay, it's going to be 7, and it's true because we have the 10 as the root node, then the left child is 5, then the left child of 5 is 3, and the right child of 5 is 7, and this 7 is the greatest item in the left subtree. Okay, it's working fine. And we swap it with that 7, the 7 is going to be the root node after the swap operation, and then this 10 is going to be a leaf node. So removing a leaf node, we just have to set it to null. And that's why the in-order traversal is going to have the 3, 5, 7, 15, 3, 5, 7, 15 in numerical ordering. What if we would like to get rid of item with a leaf node, for example? Let's get rid of the 3. It's going to be a leaf node, so we just have to get rid of it. 5, 7, 10, 15. Okay, it's working fine. What if we get rid of a node? I'm going to get rid of 7, and then if we get rid of that 5, then it's going to have a single left child. So let's save it. Removing the left child, yeah, it's working fine. 3, 10, and 15. 3, 10, and 15. Okay, we are missing the 5 because we have already removed it. And let's consider another fact. I'm going to insert, for example, 20. And if we get rid of the 15, then we should get the right case. Yeah, removing the right child. So the numerical ordering after the delete operation is 5, 10, and 20, because we have got rid of 15. Okay, so it's working fine. This is how we implement the remove operation with the 3 cases: when we have a single child, when we have a leaf node, when we have 2 children. If we have 2 children, then we are going to reduce the problem to one of the previously implemented cases. Okay, so that's why there's again a recursive method call, but here we are able to handle it. We just have to return null, and here we just have to update the references. Okay, that's all about the binary search tree. Thanks for watching.